So this is our review for AP Precalculus Unit 1, Part 1. So this covers topics 1.1 through 1.6. First question here, we've got a graph. It's on a closed domain, so from -6 to 6, and we're going to use the graph to identify where are we increasing, decreasing, concave up, and concave down. So our graph is going down, then up, then down. So it's increasing from here to here. So -2 is less than x is less than 2. These can be inclusive or non-inclusive. Both would be acceptable. It's decreasing from here to here and here to here. So from -6, because I would include that one, to -2, and from 2 to 6. Concavity. Okay, so our graph is concave up, and then it's concave down. And that change is occurring right about there. Okay, so it's going to be concave up from -6 to 1, and then it's concave down from 1 to 6. Now these endpoints, I'm okay if you don't include them, but those are increasing, decreasing, concave up, concave down. So let's look at another one. All right, increasing, so we're going down and then up. So from 1 to about 4.5, and it's decreasing, then it's increasing there from 7 to 8. Our graph is decreasing from -1 to 1, and then from 4.5 on down to 7. Okay. Concavity, because that's 7. Okay, our graph is concave up, concave down, concave up. So it's concave up from -1 up to 3. And then it's concave up again from 6 to 8. And it's concave down in this middle guy from 3 to 6. Now we're looking at rate of change. So for each scenario below, determine if we have a positive rate of change or a negative rate of change. So the number of people on an airplane and the number of empty seats. Well, if there's more people on the airplane, there's going to be less empty seats. So this will be a negative rate of change. The price of gasoline and the amount it takes to fill your gas. Well, if their cost is more, it's going to cost you more. So that's going to be positive. GPA and your class rank. Hopefully, if your GPA goes up, so does your class rank. Okay, now we're going to find the average rate of change. So let's review that formula. Okay, so we have the average rate of change on a closed interval AB is our slope of the secant line, but we're going to write it as f of b minus f of a over b minus a. We need to find the function values at a and b. Those go in the numerator, our x values down here, and do the calculations. All right, so we're finding these on the closed interval -2 to 2. So I'm going to start with my difference quotient. So we want f of 2 minus f of -2 over 2 minus -2. So we need to go find those function values. So we'll plug in 2, which gets me a 7. Plug in -2. Which gets me a -1. So f of 2 is 7 minus -1 over 4, which gives me 8 over 4, and we want to simplify that to 2. Okay, our next equation. Start with our difference quotient, g of 2 minus g of negative 2 over 2 minus negative 2. Find our values. So f of 2 is going to be 2 plus 3 over 2 minus 1, which is just going to be 5. F of negative 2 is negative 2 plus 3 over negative 2 minus 1. So on the top we get 1, on the bottom we get a negative 3. So we've got 5 minus negative 1/3 over 4. We'll get a common denominator here. So this will be 15 plus 1 over 3. So 16 over 12, which reduces to 4/3. We can get our values from a table. So I'm still going to start with my difference quotient. K of 2 minus K of negative 2 over 2 minus negative 2. From my table, K of 2 is 5. K of negative 2 is negative 2. So it's 7/4. And lastly, finding the rate of change from a graph. So my graph of P, so start with, you guessed it, the difference quotient. P of 2 minus P of negative 2 over 2 minus negative 2. P of 2 is 3. P of negative 2 is 1. So we get 2 over 4, which is 1/2. And this one's a good one to demonstrate. If I were to draw that line segment from those two dots, this absolutely has a slope of positive 1/2 because the average rate of change is the slope. Okay. The next set of problems deal with the relationship between features of the graph and the rate of change. So I want to kind of summarize this idea. So if f of x is increasing, and we just did examples to show increasing, decreasing. If the graph of f is increasing, that means the rates of change are positive. Okay, for an illustration, if I have an increasing graph, and I'm going to use tangent lines, the slope of any tangent line there is going to be positive, and rate of change is the slope. If our graph is decreasing, then our rates of change are negative. So if I have a decreasing graph, any slope, any rate of change is going to be negative there. If our graph is concave up, then my rates of change are increasing. So if I have a concave up graph, if I have a rate of change here, we're going from a negative to a 0 to a positive, and this can occur on a strictly increasing or strictly decreasing interval as well. But if the slopes are getting bigger, so we're going from negative to 0 to positive, the rates of change are increasing, and we have a concave up graph. If it's concave down, the rate of change is decreasing. So concave down, this slope is bigger than this slope is bigger than this slope. So the slopes are getting smaller, they are decreasing. So when we're doing our investigation, you can kind of go either way, depending on how the question is written. For example, let's say we know the graph is concave up, then we can say that the rate of change is increasing. Maybe we know that the rate of change is increasing, which means our graph is concave up. So depending on the scenario, you might be going from here to here or here to here. So let's look at some examples. Okay, so we have a graph, A, B, C, D, E are some clear points here. On which of the following intervals is the rate of change negative and decreasing? Okay, so let's think about what that would say to us about the graph. If the rate of change is negative, then my graph is decreasing. If my rate of change is decreasing, then my graph is concave down. So I'm looking for decreasing and concave down. So this is decreasing concave up. This is decreasing concave down. So D. Okay, same graph. This time we're looking for on which of the following intervals is the rate of change positive and decreasing. So that tells me on the graph, if the rate of change is positive, we're looking for the graph to be increasing. And if the rate of change is decreasing, that is again concave down. So increasing is this whole portion here. The part of it that is both increasing and concave down is from C to D. Okay, for this next one, new graph, and we are asked on what intervals is the function increasing at an increasing rate. So this means the function is increasing and the rate of change is increasing. So we're looking for it increasing and concave up. So we're increasing and concave up starting at -2 until we get to that inflection point at 1. Same graph. Now we're looking for where the graph is increasing at a decreasing rate, which means we're looking for it to be concave down. So still increasing here, but it's increasing and concave down from 1 until we get to 4. Okay, so we're going to describe the rate of change based on these graphs. So this is increasing and concave up, which means my rate of change is positive and it is increasing. So if I go here, positive and increasing is that. This graph is decreasing and concave down, which means my rate of change is going to be negative and it will be decreasing. So we're looking for negative and G is decreasing and the rate of change is decreasing. For our next topic, we are looking at a table of values and we're going to determine whether the function is linear, quadratic, or neither. For the graph to be linear, the average rate of change between any points must be the same. So we don't necessarily need even intervals for that. These all do have even intervals, so we're good. But if the rate of change is the same, then we have a line, which makes sense. Rate of change is the slope. On a line, the slope is the same no matter where you look. Quadratic, over equal length input values, okay, meaning they're the same distance apart. If the rates of change are increasing at the same amount, then it is quadratic. So we're going to describe that as the rates of change are linear. They're going up by a constant value. If neither of those happen, then we're just going to call it neither. All right, so let's calculate some rates of change. So we're going here to here, here to here, here to here. So we have -2 minus 2 over 0 minus -2. So I'm just doing y2 minus y1 over x2 minus x1. This gives me -4 over 2, which is -2. Here, 2 minus -2 over 2 minus 0 gives me 4 over 2, which is 2, which means our graph is not linear. We've got 14 minus 2 over 4 minus 2, which is 12 over 2, which is 6. Okay, so the rate of changes are increasing, and they're increasing by a set value. So this is going to be quadratic. And our reason is that the rates of change, I guess we should say average rates of change, is linear. Okay, here we've got, so -1 minus -3 over -1 minus -2. Now these denominators are all going to be 1 because we're going up by 1, so we might save ourselves a little time on that. So this will be 2 over 1, which is 2. Here I'm going up 2, so 1 minus -1 over 1 is 2. 3 minus 1 over 1 minus 0 is 1. And 5 minus 3 over 1 is 2. So we get 2 for all of these. So this is linear because my rates of change are constant. Okay, here we're going to have 7 minus 3 over 2 minus 1, which is 4 over 1. 8 minus 7 over 3 minus 2 gives me 1 over 1, or 1. And then 11 minus 8 over 4 minus 3 gives me 3. So they're not going up by the same value. They're not the same value, so this would be neither. So for this one, -1 minus 1 over 2 minus 0 would be a -2 over 2, which is -1. -7 minus -1 over 4 minus 2 gives me -6 over 2, which is -3. And finally, -17 minus -7 over 6 minus 4 would be -10 over 2, or -5. These are going up by a steady rate of -2, which means we are quadratic. And my explanation again is that the rates of change are linear. Okay, over equal input values. If these were not equal, then this doesn't show us anything. But okay, now we're going to look at these table of values to determine concavity. And just like with the graphs, if the rate of change is increasing, our graph is concave up. If our rate of change is decreasing, our graph is concave down. So these are all going to be this over 1. And I'm really just looking for, are the rates of change increasing or not? So here I'm going up 2. Here I'm going up 4. Here I'm going up 8. Here I'm going up 16. So the rates of change are increasing, so our graph is concave up because my rate of change is increasing. Okay, let's do this again. Got -4, -4, -4, -4. Not increasing or decreasing. And in fact, and I maybe should have, if these are the same, it means we have a line. If you have a line, there is no concavity. So this is neither. Your reason, you could either say the function is linear or that the rate of change is constant. Okay, going down 3, down 5, down 7, down 9. So this is quadratic since the distance between these is decreasing at a constant. But for our purposes, the rates of change are getting smaller. So it's concave down. Okay, because the rate of change is decreasing. do one more. Okay, going up 1, up 2, up 4, up 8. These are increasing, so we're concave up because the rates of change are increasing. All right, so here we're finding the degree and the leading coefficient. So the degree is going to be the highest power, which in this first one is 7. The leading coefficient is the coefficient in front of that. So in this case, that's -5. Here, it's kind of written a little bit funny, but our highest power is going to be 10, which makes the leading coefficient 3. For this one, I'm going to go ahead and distribute. So I get 12x to the 8th minus 9x to the 5th, which means my degree is 8 and my leading coefficient is 12. Okay, so in this graph, we're going to be looking for relative mins and maxes. So relative mins and maxes are values that for their little part of the world are the smallest or the biggest. So we have relative maximums here. This is our winner for that little area. And here. So that's going to be at x equals, oh, those are the maximums. That's -4 and 5 for maximums. Sorry, I did this out of order. Our relative minimums is here. And because this one is on a closed interval on this right-hand side, it is also a relative minimum. So we have minimums at 2 and again at 6. Absolute minimums and maximums are the greatest value on the graph or the least value on the graph. So here, the smallest y value I have is right here. So the absolute minimum occurs at x equals 6. For this particular graph, since the arrows continue to show us that the graph increases without bound, that means there's not an absolute maximum on this particular graph. Next, we're going to identify points of inflection from our graph. So that's going to be where our graph changes concavity. So my graph is concave down, and then it switches to concave up. And that switch occurs here at x equals -1. It's concave down for a little bit, then it changes its mind to be concave. So it's concave up, then it's concave down, and it switches at x equals 1. Those are 2 points of inflection. Okay, we've got a graph, and we're going to identify some characteristics. So f of x is greater than 0. So that's going to occur here and here. So from -4 to x to -2, and then again from 0 is less than x is less than 1. These are non-inclusive because I don't want to include 0 in this. Our zeros are at -4, -2, 0, and 1. Next question asks for the least possible degree. Okay, the number of zeros, including multiplicities, is the least possible degree. So if I have 4 zeros, then my least possible degree is 4. Okay, for my graph being less than or equal to 0, that's going to occur here, still 0 to here. So I'm going to say -4 is less than or equal to x is less than or equal to 1. And of course, you can use the bracket notation instead. If you were to do that, it would be -4, -1 with our brackets. But that's up to you. I like the inequalities, but brackets are just fine. Our graph is greater than 0 here. So you could say this as -infinity is less than x is less than -4. You could also just say when x is less than -4. Either of those are fine. And then from 1 to infinity, or just when x is greater than 1. For the degree, we're looking at the zeros, and I have 3 zeros. Okay, so you may be tempted to say degree 3. But if the 0 just touches the graph and doesn't cross, we call that a multiplicity. Okay, now it might be, so multiplicity means we have multiple roots with the same value. If it touches and then just grazes it, that means it's an even multiplicity. So it could be degree, it could be something to the squared, it could be something to the fourth. We don't know. But at a minimum, it has a multiplicity of 2. Then we have these two other guys. So this one is also a degree 4. It's also a good idea to think about the end behavior. We know from 1.6, which we'll get to in a minute, if the end behavior is the same at both ends, then our polynomial is an even degree polynomial. So that should kind of match that. Okay, then we're going to determine the conjugate, which is simply just the opposite sign on that imaginary piece, opposite sign on the imaginary piece. We're asked to determine the degree of the polynomial. So we're looking at over equal length input values, what's happening to these values. So here I'm going to say I'm going up 2, going up 6, going up 10, going up 14. And we're looking for those successive differences to become the same. Okay, so it took 2 rounds to do that. So this is degree 2, also known as quadratic. Here I'm going up 2, up 2, up 14. Here I'm going up 38. So we're going up 0, 12, and 24. Going up 12, going up 12. So it took me 3 rounds to get there. So this is a degree 3, or a cubic polynomial. Okay, even and odd. An even function is symmetric to the y-axis. Okay, the definition is f of negative x equals f of x. So I'm gonna repeat, I've got a 3, 3, I'll reflect this whole thing over that y-axis. So you can pick points and pull them over. What this statement says is like f of 3 equals f of negative 3. So every counterpart has the same value. Odd is symmetric to the origin. So when you look at negative x, it has the opposite value as its positive counterpart. So we'll reflect this around the origin. Okay, if you're looking for kind of a strategy, you could look at the point and then the opposite y value. So if f of 3 is 3, f of negative 3 is negative 3, and so on. And finally, end behavior. Okay, so end behavior is what's happening at the ends of the graph, and we always use this, we will explain this in limit notation. So what I mean, we have the limit as x goes to infinity of f of x, and we have the limit as x goes to negative infinity for f of x. Okay, that part will remain the same no matter what function we're looking at. For this graph, as I go to infinity, this is decreasing without bound, so it's going to negative infinity. On this end, same deal. It's going to negative infinity. Looking at this graph, again, we start with the limit as x goes to infinity, and our graph is g this time. And we want to look at what's happening as we go to negative infinity. Okay, this one, as I'm going to infinity, isn't increasing or decreasing without bound. It's hitting a leveling off spot at this asymptote, so it's going to 0. As we go to negative infinity, we're going to 0. Okay, and if we don't have the graph, but we have the equation for the polynomial, we can still determine the leading or the end behavior based on the degree and the leading coefficient. Okay, so this one has an odd degree, and a negative leading coefficient. I'm going to abbreviate. Okay, so the graph in general is going to kind of look like that. So the limit as x goes to infinity is going to be negative infinity. As we go to negative infinity, we're going to positive infinity. Our last problem here I'm going to start with the reason, because that's what I'm going to work with. I have an even degree and a positive leading coefficient. Okay, so my end behavior, so this will look like that. So as we go to positive infinity of g of x, we're going to positive infinity. As we go to negative infinity, we're going to positive infinity. So that was your Unit 1, Part 1 review.